Okay, so if you would take out your notes that are behind section 6.3 that I handed out, or if you did not remember to keep those, they can be downloaded. We're skipping harmonic motion, which is the end of chapter 6, and we're going straight to section 8.3, which is partial fraction decomposition, which is something that you may need in calculus when you do something called integration, which is something you learn how to do where you're finding the area under a curve, a function. And when you do that, the function has to be in the right form for you to be able to carry out that integration. And so sometimes you have to know some tricks to change the way something looks, which is why you learned some of those trig identities. You have to be able to change the appearance or the construction of different functions so that they will easily be integrated by parts or however they need to be. So anyway, you know how to add fractions. I would hope with all my heart that you know how to add fractions. And that is you find a common denominator, which is made up of factors. And it has to have all the factors that both fractions have. So the factors here are x plus 2 and x minus 5. So the common denominator has to be x plus 2 times x minus 5. And so you would have to multiply that first fraction by x minus 5 over x minus 5, and the second one by x plus 2 over x plus 2. And when you do that, you will then have the common denominator x plus 2 times x minus 5, and you will multiply all that out, and you'll end up with this fraction, which is, that's fine. You've been doing that a long time. You're good with that. You know how to do it. But what if you have to do it in the opposite direction? What if you start with the fraction on the right side, like this? If you start with something that looks like this, and you want to break it up into a sum of two fractions, that is, seems like it would be fairly simple, but it actually is kind of complicated. So that's what we're going to learn to do. It's not hard. It's just complicated, and it's just not immediately obvious, but it's not difficult. It's just like a procedure that you learn to follow and carry out. So here we go. Suppose you have a rational expression, f of x over g of x, where f of x and g of x are polynomials with real coefficients, and g of x, of course, is not 0, and the degree of f of x is less than the degree of g of x. If you have a fraction like that, a rational expression like that, then you will be able to use this procedure, and you want to make sure before you even start. So say you have something like this, a fraction like this, the first thing you're going to want to do when you do the decomposition is that you want to make extra sure that the degree of the numerator is less than the degree of the denominator. If it's not, you're going to begin the whole procedure by dividing the numerator by the denominator. So if for some reason you have something like, x to the 5th over x cubed, of course you would want to go ahead and reduce that. You would want to divide that denominator into the numerator and get what would quote unquote be the whole number part of the problem, and then work with the fraction that can't be reduced. So that's what we want to do. So we would do that first, and then we would factor the denominator. In this case, it's already factored, so we're not going to worry about that. Then we want to set up the form for the decomposition. See the horrifying table below. That's in your notes. I'm not putting it on here, but it shows you how you're going to figure out what numerators to use. So you're going to write the original fraction, and it's already written, so we don't need to do that. And then you're going to write it as a sum of fractions using the factors from number 2 as the denominators. So we're going to rewrite that fraction. There's one for 2x plus 3, and there's one for x minus 2. Now we're going to create the numerators so that they are 1 degree less than the denominators. So using that table, if you look at that, and it won't make total sense right now, but you can see that these denominators are linear, meaning they have x to the first power. They look like a function that is a line, like y equals mx plus b, 2x plus 3, x minus 2. And now we choose the numerators to be 1 degree less than that. Well, what's a degree less than linear? Linear is already first degree, so it would be 0 degree, which just means a constant. So the numerators here in these two fractions are going to be constants, and that's what a and b will stand for. Some number, 5 or 12 or -3. They are just plain old ordinary numbers. And so that is how we would set this up, and then we'll go to step 4. So step 4 is to multiply both sides of the equation by the common denominator, which is 2x plus 3 times x minus 2. When you do that, the left side of the equation just becomes 4x minus 15 because the denominator cancels. A over 2x plus 3. The 2x plus 3 is going to cancel, and we'll just end up with a times x minus 2. And then for b over x minus 2, the x minus 2 is going to cancel, and we'll end up with b times 2x plus 3. And now we're going to multiply that out. We'll get ax minus 2a plus 2bx plus 3b. So we did that. Now we're going to set the coefficients on the left side of the equation equal to the coefficients of their like terms on the right side of the equation. So that sounds complicated, but it's totally not. Get the x's together. So ax plus 2bx. So those are the terms that have an x in them. And then get the other things, the constants here, they just don't have any x's at all, over there. If we factor out this x, we've got a plus 2b times x. And then these guys are, again, just the constants. No x's involved. All right, so this is supposed to equal 4x minus 15. If it equals 4x minus 15, well, the x term is a plus 2b times x. And so a plus 2b is basically the coefficient of x. It is the thing that x is multiplied by, which means it has to be 4. So we can write that down. A plus 2b is equal to 4. So we set that coefficient equal to its counterpart on the left side of the equation, because that has to be true. And then all you're left with over here is just some constants, just nothing. They don't have x's at all. And that part of the equation is negative 15. So negative 2a plus 3b must be negative 15. So now I have a set of 2 equations and 2 unknowns, and I can solve it. I'm going to do that by elimination. I'm going to multiply the first equation through by 2 and cancel out the a's. So when I do that, I'll have 2a minus 2a is 0, and then 4b plus 3b is 7b, and that should equal 8 minus 15, which is negative 7. So b is negative 1. And so if b is negative 1, a plus negative 2 is 4, which means that a is 6. So we've got a, we've got b, and so now we can write our partial fraction decomposition, which is this. So 4x minus 15 over 2x plus 3 times x minus 2 can be written as a sum of fractions in this way. 6 over 2x plus 3 plus negative 1 over x minus 2. So this is how you decompose this fraction. If you were to get a common denominator and multiply that out, it would equal 4x minus 15 over 2x plus 3 times x minus 2. So we solved this system of equations, and we wrote the partial fraction decomposition. All right, so now for example 1, we're just going to set up the form. We're not going to actually do the whole thing out. For the first one, we already did it. We just did it, so we're not going to do that. Check the degree of the numerator and the degree of the denominator to make sure that the degree of the numerator is less than the degree of the denominator. And that's true, so we're good. Now we're going to factor that denominator. X times x squared plus 6x plus 9. And that can be factored to x times x plus 3 quantity squared. So we factored the denominator, and now that means we're going to write some fractions with those factors as their denominators. So first fraction is going to have x. Another fraction, I won't write that one yet. Another fraction will have x plus 3 quantity squared. So why am I putting another fraction there? Well, if you have some kind of non-factorable item like x plus 3, and it is that quantity is raised to a power, you need to have a denominator with that thing to the first power and to the second power. So this one will be x plus 3 to the first power. And that's not obvious, and that's just a rule. So anytime you have some kind of expression in parentheses being raised to a power, you need to write a fraction for first power, second power, however many powers there are. If it was cubed, you'd have to write one for first power, second power, and third power, because that's how it works out. It's not that anybody made that up. It's just that's what happens when you decompose a function. When you decompose a fraction like this, that's what you end up with. Okay, so now according to that table, we need to write the numerators as 1 degree less than the denominators. If the denominator is linear, like the first two fractions, then you will use a constant. So for the first one, I'm going to put A, second one, B. And then for the third one, it seems like I would want the numerator to be linear because the denominator is quadratic. But actually, we don't consider this to be quadratic. We're really just looking at the non-factorable expression that is left there inside the parentheses. So whatever, if that is linear, we will put a constant. If it were inside the parentheses, if you had a quadratic, then you would put a linear numerator. But we'll see a problem like that next. But for this particular situation where you have some kind of expression being raised to a power, it's the degree of that expression that matters, not the power. You kind of ignore the power when you're deciding what to put in the numerator. So since this expression x plus 3 is linear, the numerator will be 1 degree less than that, which is a constant. So that's how you would set that one up. Again, start out by checking to make sure that the degree of the denominator is bigger than the degree of the numerator, and it is. So now we're going to factor the denominator, so x times x squared plus 4. And now we write two fractions, because we just have two factors here, x and x squared plus 4. And so the numerator here is going to be a constant because that denominator is linear. This denominator now is quadratic. It can't be factored in any way, and it has an x squared in it. So it is quadratic, which means the numerator needs to be linear, like ax plus b. So, but we'll use bx plus c because we already used a. We don't want to use it again. And we're not doing it all the way out. We're just setting it up. All right. This next one, you can see that you now have a quadratic raised to a power. And so you treat that just like you would a linear expression raised to a power. You write a fraction for every power of that expression. So one of the denominators will be x squared plus 2x plus 5. And the other one will be that quantity squared. And since these are quadratic denominators now, we're calling this quadratic. Remember, it doesn't matter what the power on the outside is. It just matters on the degree of the expression inside. So quadratic means linear on top, ax plus b, and cx plus d. Okay, so this is the one back from example 1. So we're going to go ahead and just do this one all the way to the end. And we already set it up. And now we're going to follow that procedure that we talked about at the very beginning. We're going to multiply both sides of this equation by the common denominator, which in this case is going to be x times x plus 3 quantity squared. When we do that, the left side, that whole denominator cancels, and we end up with 4x squared plus 10x plus 9. Now, with a over x, the x cancels, and we have a times x plus 3 quantity squared. With the b over x plus 3, the x plus 3 cancels, and we end up with bx times x plus 3. And then on the last one, we just have cx. Now, we're going to multiply it out. So a times x squared plus 6x plus 9 plus bx squared plus 3bx plus cx. Okay, if we multiply that out, we're going to have ax squared plus 6ax plus 9a plus bx squared plus 3bx plus cx. And now I'm going to get all my like terms together. So I'll have ax squared plus bx squared plus 6ax plus 3bx plus cx plus 9a. And just to make sure we all understand what the coefficients are here, I'm going to factor out the x squared here, and I'll have just a plus b. And then I'm going to factor out the x, and I'll have 6a plus 3b plus c there, and then I've just got 9a over there by itself. So if we look back up here at our left side of the equation, the coefficient on x squared is supposed to be 4, which means that a plus b has to be 4, because it is the coefficient on x squared. And then if I look at the coefficient on x, it's 6a plus 3b plus c, so that must be 10. So 6a plus 3b plus c is 10. And then the 9a is the constant, which means that it must equal 9. So 9a is equal to 9. So a must be 1, and that means that b must be 3, because a plus b is 4. And then 6a, which would be 6, plus 3b, which would be 9, plus c is equal to 10. So 15 plus c is 10, which means that c is negative 5. And so we have our a, we have our b, we have our c, and now we can write our partial fraction decomposition. To do that, I'm going to have to erase this very first line, so I have room. And I'm going to change my pen color just so we don't get confused. And so a is 1, so 1 over x plus b is 3, 3 over x plus 3, and then c is negative 5 over x plus 3 quantity squared. So this is equal to this. Okay? If we are smart, we will remember that we have to check to see if the degree of the denominator is greater than or less than the degree of the numerator. In this case, the degree of the denominator is less than the degree of the numerator, which means the first thing I need to do is divide, because there's no point in trying to decompose something that's not even really a fraction. So we're basically reducing this down to a whole number part, quote unquote, and a fraction part. So let's do that first. X cubed plus 4x divided into x to the 4th plus 3x cubed plus 6x squared plus 9x plus 4. And so x cubed goes into x to the 4th, x times, multiply, x to the 4th plus 4x squared. Oops, wrong place. It gotta go over here. Here we go. Subtract 3x cubed. 6x squared minus 4x squared is 2x squared. And then we're going to bring down the 9x. X cubed goes into 3x cubed 3 times, so plus 3 up there, and then 3x cubed plus 12x, which goes there. And so 2x squared, 9x minus 12x is negative 3x, and then bring down 4. So we have x plus 3 plus 2x squared minus 3x plus 4 over x cubed plus 4x. All right, so we're writing what this equals. The first thing that will come is the x plus 3. But since it will just get in my way, I'm going to leave it off till the end of the problem, because this part isn't a fraction, so we don't need to decompose it. We'll just put it off to the side, because even though it is part of our answer, we don't have to do anything to it. It's good to go. So this is what we have to deal with now, is this fraction. We want to decompose that fraction. And I'm just going to write over here 2x squared minus 3x plus 4 all over x cubed plus 4x. So this is x times x squared plus 4, and we already wrote one like that before. The first fraction is just going to be over x, and it's going to be a constant on top because it's linear on the bottom. And then over here we've got x squared plus 4, which is going to be a linear expression on top. Whoops, can't use a again. Bx plus c on top because the quadratic is in the denominator. And now we will just multiply both sides of that equation by the common denominator of x times x squared plus 4. And when we multiply all this out, we will have ax squared plus 4a plus bx squared plus cx. And so if we get our like terms together, we have ax squared plus bx squared plus cx plus 4a. So x squared has the coefficient of a plus b. X is just coefficient c, and 4a is our constant. So we're going to write our system of equations based on the coefficients of x squared, x, and the constant. So the coefficient of x is 2, which means that a plus b must be 2. The coefficient on x is c, which means that c must be negative 3. And the constant is 4a, which must be the constant, 4. So 4a is 4, which means that a is 1. We already know c is negative 3. And since a is 1, b must also be 1, because 1 plus 1 is 2. So our final answer will be, we'll start with the whole number part we got at the very beginning of the problem, x plus 3. And now we'll add the part that is the decomposition, which is a over x, which is 1 over x, and then bx plus c over x squared plus 4, x minus 3 over x squared plus 4. So this would be equal to this. Okay, so this is the one we set up before. We're going to multiply the whole thing by the common denominator, which is x squared plus 2x plus 5 quantity squared. When you do that, the left side won't have a denominator anymore. The right side, for the first fraction, one of those x squared plus 2x plus 5s cancels, but you're left with one of them. So ax plus b times x squared plus 2x plus 5. And then cx plus d, that whole thing, the whole denominator cancels. And so if we multiply this out, all right, so now let's just group our like terms together. So 2ax squared and bx squared, go ahead and factor out the x squared. So I'll have 2a plus b for that. And then for the x's, I've got 5a plus 2b plus c. And then I just have 5b plus d for my constant part. So looking back over at the left side of the equation, you've got 3x squared plus 8x plus 14. First thing you have here is ax cubed. There is no x cubed, but that means that a must be 0. That's all it means. There is no x cubed term, so a must be 0. So that was easy enough. A is 0. Then you've got x squared times 2a plus b. The coefficient on x squared is 3. So that means that 2a plus b must be 3, which actually means that b is 3, because 2a is just 2 times 0, which is 0. Then you've got 5a plus 2b plus c for the coefficient on x, which is supposed to be 8. And then the constant term is 14, which means that 5b plus d must be 14. 5a plus 2b plus c, the 5a goes away. 2b is 6. So 6 plus c is 8, which means that c has to be 2. And then 5b plus d is 14. So 5 times 3 plus d is 14. So d is negative 1. So we've got our a, we've got our b, we've got our c. And so now we can write the partial fraction decomposition. 3 over x squared plus 2x plus 5. And then for cx plus d, that would be 2x minus 1. And the denominator is just x squared plus 2x plus 5 quantity squared. And so that is the partial fraction decomposition for this fraction right here.